Imagine this. A towering machine, taller than the Statue of Liberty, sits on a launch pad. In an instant, it erupts into a cataclysm of fire and thunder, a scene that looks exactly like an atomic bomb detonating at its base. The ground shakes for miles, the sky turns orange, and inside that apparent hellfire, human beings, riding what seems like certain death straight into the heavens. Every time a rocket lifts off, it appears to be exploding. Yet these machines don't just survive. They deliver crews safely to orbit with astonishing reliability. How is that possible? What hidden world of precision and genius turns this deadly-looking chaos into one of humanity's greatest engineered triumphs? Today, we step behind the guarded gates of rocket factories. We expose the secrets that keep every fiery launch genuine, controlled, and survivable. You're about to discover truths almost no one outside these clean rooms has ever seen. Why rockets explode with fire on launch, the engineering secrets behind flames, and how astronauts survive. The modern space industry is booming like never before. In 2025 alone, over 200 orbital launches took place worldwide. Companies like SpaceX, Blue Origin, Rocket Lab, and national agencies are launching more frequently than at any point in history. What was once the domain of superpowers is now a global enterprise pushing humanity toward multiplanetary life. But it wasn't always this way. Early rocketry was plagued by failure. In the 1950s, failure rates exceeded 70%. Rockets exploded on pads, veered off course, or disintegrated mid-flight. Lives were lost. Billions vanished in fireballs. Yet from those ashes emerged today's precision, a testament to relentless engineering evolution. This isn't just about fireworks in the sky. Reliable rockets power satellite communications, climate monitoring, national security, and our dreams of Mars colonies. Understanding their hidden truths reveals the pinnacle of human ingenuity, mastering fire, gravity, and the void. Now, let's walk the factory floors where these marvels are born. Chapter 1. Inside the rocket factory, the extreme cleanliness and precision most people cannot imagine. You think your kitchen is clean? Try walking into a modern rocket factory. These facilities make hospital operating rooms look filthy. At places like NASA's Michoud Assembly Facility or SpaceX's factories, the air is filtered to ISO Class 5 or better, meaning fewer than 100 particles per cubic foot larger than 0.5 microns. One speck of dust could cause a catastrophic failure thousands of miles up. Why such insane cleanliness for something that's going to be blasted by fire anyway? The answer lies in materials science. Rocket structures use ultralight aluminum lithium alloys and carbon composites. These are incredibly strong, but vulnerable to microscopic flaws. A single contaminant can create a stress riser, a point where metal fails under immense pressure. Engineers machine tank sections with tolerances tighter than a human hair. Friction stir welding joins panels, a process that creates bonds stronger than the parent metal itself. No traditional welds that could crack. Some factories use temperature-controlled rooms where parts expand and contract predictably, allowing machines to hit tolerances within microns. 1 degree off, and a critical component is scrapped. Workers undergo rigorous protocols, no cosmetics, strict clothing changes, constant monitoring. Human stories emerge here, veteran technicians who spend decades perfecting one weld, knowing a single mistake could end a mission. But even this precision is just the beginning. What if the very fuel that powers the beast is also its greatest threat? Let's go deeper. Chapter 2. Why the fire is necessary and how it's perfectly controlled. Rockets don't burn like your car engine. They use extreme chemistry. Most use liquid oxygen LOX as oxidizer and kerosene or methane as fuel. These are stored at cryogenic temperatures, LOX at around minus 183 degrees Celsius. When mixed and ignited in the combustion chamber, They release energy violently. Why does it look like an uncontrolled explosion? Because it is a controlled explosion, thousands of times per second. Newton's third law in action. Hot gases expelled downward at enormous velocity push the rocket upward. The fire you see is superheated exhaust, often with shock diamonds forming beautiful patterns in the plume. SpaceX's Merlin engines, for example, produce over 650 knots of thrust each. 9 of them on a Falcon 9 generate more than 7 million pounds at liftoff in some configurations, yet each engine is throttled precisely by computers. Little known truth. Before ignition, hydrogen or other gases are vented and sometimes burn off, creating the dramatic fire above nozzles effect on vehicles like the Delta IV. It looks terrifying but is normal and designed. Engineers test fire engines hundreds of times. Additive manufacturing, 3D printing, now allows complex cooling channels inside nozzles that prevent meltdown, cooling the engine while producing temperatures hotter than the surface of the sun. Yet the real magic happens in the first seconds of flight. Chapter 3. The explosion physics. What's really happening in the first 8 seconds of launch? Those first 8 seconds are the most dangerous. Engines ignite in sequence to manage loads. The rocket is held down by massive clamps until thrust exceeds weight. When released, it climbs, slowly at first, then accelerating. The visible explosion is a rapid expulsion of combustion products. Pressure in the chamber can reach hundreds of atmospheres. Nozzles shape the flow for maximum efficiency via the Laval design, converging and diverging to accelerate gases to supersonic speeds. Rockets don't explode upward. Failures usually involve structural breakup or commanded destruct, flight termination system, that disperses propellants safely. The big fireball is often post-failure deflagration. Modern launch success rates hover around 95 to 98% overall, with manned missions far higher, under 2% failure historically for crew flights. But what about the people inside? Chapter 4. The human factor. How astronauts are protected inside this apparent inferno. Astronauts don't feel an atomic bomb. They feel a sustained, powerful push. G-forces peak around 3 to 4 G during ascent, manageable thanks to vehicle design and training. Compare that to fighter pilots pulling 9 G turns. Seats are oriented so acceleration pushes astronauts into their backs. Special suits and harnesses prevent blood pooling. Centrifuge training prepares them for the crushing sensation. What you never knew. The capsule is a fortress. Vibration dampeners, acoustic insulation, and redundant systems protect against the roar, over 140 dB, and shaking. The inferno stays outside. Heat shields and thermal protection handle re-entry later. But launch is about thrust vectoring and structural integrity. Human stories. Veterans describe it as a kick in the pants, followed by smooth acceleration once in thinner air. The real guardians, though, are the invisible systems ensuring nothing goes wrong. Chapter 5. The hidden factory systems that prevent disaster. This is where genuineness is forged. Factories employ failure mode and effect analysis, FMEA, statistical process control, SPC, and Six Sigma level rigor. Every part is tracked with digital twins, virtual models updated in real time. Non-destructive testing. Ultrasound, X-ray, dye penetrant. One tiny void in a weld, rejected. Even with all this, one invisible enemy nearly ruined everything in early programs. Combustion instability. Oscillating pressures that could tear engines apart. Solved through thousands of test firings and baffles. SpaceX's make requirements less dumb. Delete parts, philosophy streamlines while maintaining margins. Engine out capability on Falcon 9 means it can lose engines and still succeed. Shocking revelation. Production rates have skyrocketed. SpaceX once built 1 Falcon 9 per month. Now they produce dozens annually with high reuse. But even perfection has its tests. Chapter 6. The invisible enemy that almost destroyed everything. Here's the twist that raises the stakes. The greatest threat isn't fire or fuel. It's resonance. Vibrations that can shake a rocket apart like a tuning fork at the wrong frequency. In the 1960s, several vehicles suffered pogo oscillation, longitudinal vibrations that nearly doomed Apollo. Modern rockets use active dampers, sensors, and real-time throttling to kill these modes before they amplify. One little-known fact. Many explosions you see in tests are intentional destructs to validate safety systems. The factory protocols ensure that even in failure, harm is minimized. This precision is what allows the journey from factory to pad. Chapter 7. Launch Day. From factory gate to pad and ignition. Transported horizontally or vertically, the rocket is checked again at the pad. Propellant loading is a ballet of cryogenics. Tanks chilled, vapors venting. The countdown is choreographed tension. At T0, the controlled release of chemical energy begins. The first seconds. Max Q, where aerodynamic stress peaks. Then staging. The upper stage ignites in vacuum. Payload deploys. You won't believe this. Some boosters return and land, engines reigniting precisely after re-entry. Human engineering conquering gravity twice in one flight. Chapter 8. The full picture of why it works. The fiery spectacle isn't chaos. It's the visible manifestation of perfected physics, materials, and human will. Every weld, every sensor, every test ensures the product remains genuine, a reliable bridge to the stars. We've turned potential catastrophe into routine, from 70% plus failure rates to near perfect reliability. Humanity has mastered fire not to destroy, but to ascend. These rockets symbolize our refusal to be bound by gravity. As we stand on the cusp of routine spaceflight, remember, behind every flame is precision beyond imagination. The future is not coming. We are building it, one controlled explosion at a time. What surprised you most about the hidden world of rockets? Drop your thoughts below. If you want more deep dives into engineering marvels, hit subscribe and turn on notifications. We're just getting started.
And here we go. Hydrogen burn off igniters initiated. 7, 6, 5. Four-stage engine start. 3, 2, 1. Back to the moon and